Okay, so I'm going to do out number 40 from the textbook questions from chapter 3. And this is a typical combustion analysis problem. So whenever we're asked to find the formula, we always need to find the mole ratios of each of the elements in our formula. So a lot of the times when we first started this chapter, we were given those amounts either as grams of each particular element, or we were given percents of each particular element, and we were able to turn those into moles and then get the mole ratio. In this circumstance, we don't have the grams or the moles of each individual element, but we do have masses of products in a reaction. So if I take a look, they tell me that I have some unknown compound that contains carbon, hydrogen, and oxygen. And they tell me when it's combusted or burned, meaning when it reacts with oxygen, I'm getting carbon dioxide and I'm getting water. And they give me the amounts of carbon dioxide and the amounts of water. So in order to do this, I can notice, and I color-coded it so it was easy to see, all of my carbon is going to end up in the carbon dioxide. So I can actually use the grams of carbon dioxide to isolate just the mass of carbon. So that's where I'm going to start. So let's get the mass of just carbon from the carbon dioxide. So I have 12.24 grams of CO2. And I'm going to need a conversion factor. I want grams of carbon dioxide in the bottom so that it cancels out. And I want grams of carbon in the numerator so that that's what I'm left with. I can use my formula to understand what I can do in this conversion factor. I know that the mass of 1 mole of carbon dioxide is 44 grams. And in every 44 grams of carbon dioxide, I also know that there will be 12 grams of carbon because there is 1 C, which weighs 12 grams, in every 1 CO2 mole. So in my calculator, I can do 12.24 times 12 divided by 44, and I end up getting 3.338 grams of CO2 cancel out, so now I'm in grams of just carbon. There's another way I could have gone about doing this if you're more comfortable. Again, I could start with 12.24 grams of CO2, and I want to isolate the grams of just carbon. If I look at the CO2 formula, those subscripts are on a mole basis. So what I can first do is I can go from grams of carbon dioxide to moles of carbon dioxide, and I can do that using the molar mass. For every 1 mole of CO2, there's 44 grams of CO2. Grams of CO2 cancel out, and I'm now in moles of CO2. I don't want CO2, I want just carbon. So I can use another conversion factor. In 1 mole of CO2, there's 1 carbon in the formula, so there is 1 mole of C. I'm just getting this from my subscripts in my formula. And I can do one more conversion factor because I don't want moles of C, I want grams of C. In every 1 mole of C, I can look on the periodic table and I see the atomic mass of carbon is about 12 grams. If I do this out in the calculator, I'll end up getting the same exact number. So whichever way you're more comfortable doing it, if you want to do it in one step like the first one, I'm kind of thinking of this conversion factor in the first one almost like a percent by mass, where the mass of the part in the numerator, 12 grams, I have the mass of the whole thing in the denominator, and I can use that as a conversion factor. Or, like in the one on the bottom, I can go from grams into moles of CO2 into grams of, into moles of carbon into grams of carbon. So that's just my first step. Now I've gotten grams of C. Let's start thinking about how I can get another element. I don't just have carbon in my initial compound, I have hydrogen. If I look at my top reaction, all of my hydrogen is going into my H2O. So I can do the same process, but isolate the H, the grams of just hydrogen, from the H2O. So let's start doing that. And I'm just going to leave the grams of carbon at the bottom so I keep it there for my reference because I'm going to need that later in the problem. So I start with 2.505 grams of H2O. That is in my problem statement. And again, I can convert into grams of just hydrogen. I want grams of H2O on the bottom. I want grams of hydrogen on top. And I can use in my conversion factor how many grams of H are in every mole of H2O. So 1 gram of H2, or 1 mole of H2O, weighs 18 grams. And in that 18 grams, 2 of the grams are hydrogen because there are 2 hydrogens in H2O given the formula. Grams of H2O cancel out, and in my calculator I do 2.505 times 2 divided by 18, and I get 0.2783 grams of hydrogen. Again, I could have done this the other way. The longer way, I could say, again, starting with they gave me of H2O. Okay, I can convert this into moles because I know my formula is on a mole ratio. For every 18 grams of H2O, there's 1 mole of H2O. Then I can convert into moles of just H. And I could say, okay, there's 2 moles of H in every 1 mole of H2O because of that subscript. And then I can finally convert these moles of H into grams. The molar mass is just 1, so 1 mole of H always weighs 1 gram. And I would end up getting the same units and the same answer, 0.278 grams of H. And I'm just going to write that on the side. So now I have, oh, I need the eraser. So now I have the grams of hydrogen, I have the grams of carbon, but there's one more thing in my formula. Not only is there carbon and hydrogen, but there's also some oxygen. But I'm in luck. I have the mass of the whole thing. I have 5.287 grams of the whole thing, the CXHYOZ. And I'm just going to change that to color. And I also know that in that amount, I have 3.38 grams of just the carbon. So I can subtract that out. I also know that I have 0.278 grams of the hydrogen, and if I take those out, I could be left with just the oxygen. So I'm subtracting the carbon out of my original, the hydrogen out of my original, and I'll be left with just the oxygen. I get 1.671 grams of oxygen. Now I've isolated each mass of each element in my compound, but I'm still not done. I need to get the formula, and formulas are always on a mole ratio. So now I've got to take all these grams and mole them out. So I've lined up my grams that I have of each, and I'm going to take each and mole it out using the atomic mass that I find on the periodic table. So for oxygen, it is 1 mole of O in every 16 grams of oxygen. Grams and grams cancel out, and I'm left with 0.1044 moles of oxygen. I can do the same thing for carbon, except I'm using the molar mass of carbon, which is 12.0 grams of carbon in every 1 mole of carbon. Make sure that your molar mass is always next to the G in your dimensional analysis, and I end up getting 0.2782 moles of C. And lastly, for hydrogen, it's really easy because it has a mass of about 1 gram in every 1 mole. Grams cancel out, and I end up getting about the same number. At this point, I essentially have my subscripts. If I was writing this out, I'm going to lead with C as I have in the formula above. It would be as if carbon has a subscript of 0.2782. It would be as if the hydrogen has a subscript of 0.278, and it would be as if the oxygen had a subscript of 0.1044. Now, this is not the way we're used to seeing formulas, nor is this the convention for writing formulas. We write our formulas with simplest whole numbers. So we've just got to do some manipulation to get these into whole numbers. And in order to do that, I'm going to divide each of these by the smallest value, which in this case is 0.1044. When I do that, a lot of the times I'll get into whole numbers right away. But if I don't, I might have a little further manipulation to do. So when I divide 0.2782 from the carbon subscript by 0.1044, I actually end up getting about 2.67. Same thing for hydrogen, somewhere around 2.67. Oxygen, since I'm dividing the number by itself, I get a subscript of 1. So what I say to do now is to just try multiplying by different integers to see the smallest integer that will give all whole numbers. So let's say I try to multiply these through all by 2. Right, in my calculator I get 2.67 times 2, and I get 5.34. Okay, still not a whole number. Okay, let's try multiplying these through by 3. Okay, 2.67 times 3. Okay, I get about 8. That's perfect. So I get C8, H8, O3, and there's my empirical formula. So again, to summarize, I'm using the products to isolate my masses of each individual element. The oxygen I found isolating it by subtraction. Then I convert the masses of each element into moles of each element. Then I can use those moles to come up with the mole ratio or the subscripts for my formula.